Here we are. Welcome to the physics video lecture. Once again, physics 4B, video lecture 24. We have a lot to talk about today. I had a large list of homework problem requests. I'm going to write them all up on the board and see if we can deal with them all. And let's go ahead and do that. So let's just call this review. We're looking at chapter 26, problems 25 and 26. Chapter 27, this is quite a few, 16, 23, 34, 38. And then from the next homework, 49, 82, and 93. And then in addition to all that, quiz number 11 plus quiz 11. So let's see what we can do about these. For problem 25 and 26. 26, I'm pretty sure I did in the lecture. Yes. 26 I did in the lecture. Okay. That was about the force on a wire that's bent and it just turns into the force on the straight segment. So just look that one up. 25 is interesting. Force on a current carrying wire of this type. So we have a semicircular wire, radius r, and the current's going to go counterclockwise. And we have a B field, and these are x and y axes. We have B field coming out of the board everywhere. Okay, so B field out of the board. And we want to show that the net force on the loop is 0. And that'll be interesting because if the net force is 0, that doesn't mean the net torque is 0. Let's think about the force here. F equals IL cross B. I'll just call this point part 1. This would be for down here at the bottom. Okay. So IL is clearly pointing this way. B is out of the board, right? Yeah, B's out of the board. So when you turn that into B, you're getting a force in the down direction. Okay. So IL cross B equals I times 2R times the magnitude of B, and it is in the, what I say, down, so negative J hat direction. Okay. Now the force for this curved segment is a little more complicated, and what we'll do is write dF is equal to I dr cross B. And what is dr? Dr is always a little infinitesimal as we move along the arc. So those are all little drs. Okay. So we have to ask, what is r? So r, we can say, is a vector r cos theta r sine theta, because we are on the arc of radius r at all times. So dr, this is a vector, would be the vector minus r sine theta, comma, r cos theta, d theta. Okay, that would be that little dr. And this ordered pair, actually, we need 3 space to do this properly, so we'll just put 0 for the z component, 0 for the z component, d theta. So that is a dr vector. And now we have to do dr cross b. So next, df is equal to I dr cross b, okay, and that vector b, see, that's why we need the z-axis. The z-axis is coming out of the board, so the vector b is equal to 0, 0, b, like that. So now you have to do that cross product, and since you have a magnitude b here, we can do this. df is equal to I r b, those are the magnitudes, and then we would have the what's left of the dr cross the b here would be this vector minus sine theta cos theta 0 crossed into 0, 0, 1. So that cross product is going to give us I r b, and I have here cos theta b I hat, cos theta, forget the b, I pulled that out, cos theta I hat plus sine theta j hat. Okay, so those are the two vectors I hat and j hat, and this is an integral. Now if you integrate these, so now integral df, this vector, and what you're going to do is integrate your theta. I didn't draw the theta in here, but you know, any point here had a theta. So you're going to integrate the theta from 0 to pi. Okay. Integral, I'm just going to write d theta 0 to pi of everything that's in there. You're going to have the IRB, the integral of the cosine theta from 0 to pi is 0. The integral of the sine theta from 0 to pi is going to be equal to 2, and plus sign will be maintained because j hat in the plus direction. So you'll get the 2 out, you'll have 2IRB, and that's what we had before, 2IRB, except instead of minus j hat, it'll be plus j hat. So I hope that suffices. It's an interesting problem. And that means that the two forces are equal and opposite, and therefore the net force is 0. Now, depending upon the orientation of a loop like this, you can get a net torque. And we get to motors and stuff. Not today, maybe next time. We'll return to that idea. So yeah, this is a good problem. So I just described it. You integrate over cosine, you get a 0. Integrate sine from 0 to pi, you get 2, and there's your 2IRB. Good. So that takes care of 25. Now, chapter 27, problem 16 is also very interesting. 27:16. So the idea here is that we've got a proton, mass of the proton, and E, and it's being orbited by an electron, and the radius of the orbit is r, and that was given in the book. Okay. And the thing is, it's orbiting so rapidly, we can think of that as being a current. Okay. Now the current, you can think of it in the following way. You can think of it as, remember, it's charge per time, but this thing is a periodic motion, so it's actually E over T. Okay, electron charge divided by the period of the orbit. You could also think of it as, and this is equivalent, E over 2 pi r, because that would then be a linear current density, charge per length, and the length is just the whole circumference of that orbit. So E over 2 pi r times V, okay? Current density times V, that would give you a charge per time, okay? And in fact, this is equivalent. 2 pi r divided by V is the period. So these are equivalent statements. So I'll write note. V times t is equal to 2 pi r when you have something going in a circle. So that's your current, and the question is, what is the speed v? What is the speed v of that electron that's orbiting the proton? And you can get that. So continuing this problem here, to obtain V, so the orbital speed of the electron, we use centripetal force. We say F centripetal, or I'll write it the other way around. We say mass times centripetal acceleration is centripetal force, and in this case, that's mv squared divided by r from our uniform circular motion equals q, it's the force. So it's q1, here, let's go ahead and write it this way. It's q1, q2 over 4 pi epsilon naught r squared, okay? That's Coulomb's law, okay? But of course for us that's E squared over 4 pi epsilon naught r squared, or we can call it k E squared over r squared, whichever form of the constant you choose, okay? But let's just underline what's important. We have this equation equals this equation, okay? So you can solve for V. So consider it done, right? Solve for V, got that. And then what were we asked to do? Well, we wanted to know the magnetic field at the center, and then you just look up the formula for the magnetic field of a current loop of radius r. And finally, B field at center of loop of radius r that's carrying a current, and then you're done. So that's a very interesting problem. Okay, moving right along. Let's see what we have here. 23. 23 was the Helmholtz coils. That's just setting it up and taking the derivatives. I'll just declare that one done. Because you have to take several or a few derivatives, just derivatives. How about problem 34 and 38 of chapter 27? I'll do 34, 38. It's very similar. Okay, now we're talking about the field of a wire, and we know the field of a long wire we get by wrapping our fingers around it. The currents in the direction of our thumb, and the field as these concentric circles in the direction of our finger. So what we have as a top view, okay, I gotta find 2734. Yes, okay, so 2734, we've got this equilateral triangle. We'll just label it with length A. So we have wires on this equilateral triangle. And this one is, we're asking what's going on at this point. So this is separation A and A. They told us 10 centimeters. Okay, we don't care what the length is. Okay, so that X means that the current is into the board. So it curls around like this. In particular, if I take this one first, the field, which makes these constant, circular field, is going to be tangent. Let's move this to the left a bit. So it's really an equilateral triangle. So yeah, what's the direction of the field going to be? It's going to be 90 degrees to that. Okay. And we're going to get the same thing here, 90 degrees, because it just, this one's on a circle, likewise this one here. Because the distances and the currents being the same, they're at the same, pretty sure the currents are the same. Yeah, each current's 15 amps. Okay, so now we have to know what's the angle in here. And since this is 60 degrees, we know that this is 30 right here, okay? And from that, 30, and this is 60, another 30 right there. So we have 60 degrees in this triangle as well. Okay. So now, we see by the symmetry here, the up and down components are going to cancel, and we're going to end up with a resultant vector that goes twice this length here. So B magnitude of this blue vector here is going to be 2. We'll have mu naught I over 2 pi a for the magnitude on that circle, radius a. Mu naught I over 2 pi a. 2 of them, and it'll be cosine of half that angle, which is 30. Cosine, okay. Cosine of 30 degrees. And only then would you want to plug numbers in, right? We don't even want to plug numbers in. That's fine. And the other problem was similar, so I'll go ahead and declare victory for that one as well. Okay. We have 49, 82, and 93. 93 I looked at maybe not long enough. There may have been a problem with the answer in the back of my book. So I'm going to skip 93, but we'll look at problem 49. Cylindrical shell, that's an interesting one. Okay. Very similar. Let's see what we have on problem 49. So we have a cylindrical shell, inner and outer radii, current parallel to the central axis. Okay, so what we have is, this is a top view. We've got radius A, radius B, and the current is flowing uniformly between the radii A and B. And we're looking on end, at a long wire, but we're looking at it on end. We don't care what the direction is, one way or the other. So here's what we know. We have Ampere's law. Integral B ds, I'm using S this time, not R, closed contour integral, is equal to mu naught I that flows through the surface bounded by this curve. So if we're doing a curve inside, so R, when we're calling it capital R, so R less than A, no current flowing there, B is equal to 0. Now, if R is greater than B, okay, so if we're out here, then we just do the basic B times 2 pi R is equal to mu naught and the total current that happens to be flowing through this annulus, right, between A and B. I'll just write I total. And we're given I as I total, so we can declare victory there as well. So the interesting one is when we're in between the two. So let's go ahead and imagine we're somewhere in between here. Then as always, the left side of our integral, so here we have A less than R less than B. Let's send this up here. So yeah, we're choosing those circular paths there, and the direction of the field is going to be the straight wired type of field based on the symmetry of the problem. So yeah, we still have our, for A less than R less than B, we still have B times 2 pi radius. We've got mu naught. But now what do we have for the I enclosed? Right, it's the I enclosed within that. So we could say it is a current density times that area. So that would be a okay. Current surface density times the area. Okay, so we've got a rho. Could use sigma, but I'm just going to use rho. And the area inside this thing, that would be from the radius R down to the radius A. That would be pi R squared minus pi A squared. So the question is, what is that current density? But rho is the total current divided by the total area here, which is pi B squared minus pi A squared. Right? I'm just taking the area minus the area, subtracting the two. So I can substitute rho for that, and now I get B is equal to mu naught, I'll divide by the 2 pi radius, mu naught over 2 pi R, and then I've got that rho, which is I, and I'll write this down next, but I'll have the pi R squared minus A squared, and in the denominator I'll have the pi B squared minus A squared, and that's why the pi cancels, but I'll leave it in there right now. So yeah, that's the answer. Very interesting problem. And when R is equal to B, B's top and bottom cancel, and you just got mu naught I over 2 pi R, and from then on, you just get yeah, you just get that solution all the way on out. Okay, good. So that was 49. 93, I wasn't sure about if the book made an error, so I'm going to ignore that one. And what about 82? Do I have anything for 82? 82, I'll just say briefly, if you want the B field, you know, at this center point here, and what are the directions they gave us? This way. it's really going to be this fraction of 2 pi of an entire circle, of d field for an entire circle, minus that same fraction of the inner one, or depending on the signs, they'll have different signs. Okay, good. So let's talk about quiz number 11 as well, and then we'll be through with this. If you still have questions about these, go ahead and send me an email. So what was quiz 11? Ah yes, quiz 11, this was a good one. So on quiz 11 I had that picture, and what did we have? We had a charge entering a region of B field. So we've got a charged particle, m, q, and it has some speed, right? And it is moving in this direction. As soon as it enters the region on the right here that has B field into the board, uniform B field into the board, it bends into a semicircular arc of radius r, and then it zips out the same direction it came in. Okay. So what we have there, something that we just had similar problems, centripetal, this is a centripetal force, and so it is mv squared over radius is equal to qvb. So what we're going to solve for is the radius. I see I have lowercase r on my picture, so we'll go lowercase r. So we're going to solve for r. So r is equal to mv over q times b, because we cancel one of the b's. And now we ask, what happens if we change m by a certain multiple, v and q by a certain multiple? So we left b the same. So if this is r initial, or the first r, r1, r2 is equal to, and I just picked some numbers off of the program, right? The program gives every student their own unique set of numbers. So m goes to, in this case, 4.3 m, v went to 2.3 v, and q went to 7.8 q. So 7.8 times q, and b was the same. So what happens is you can pull out that 4.3, 2.3, 7.8 as a factor in front of the original mv over qb. And when you multiply these numbers out, then that is the multiple times r1, right? It's this multiple, and that's r1. So that factor was what you were supposed to enter in as your answer. Okay, good. That is our review for this time. Yeah, let me know if you have more questions, but we'll move on. Let's consult the clock. Okay. Okay, what's happening now, I'm picking up where I left off with the laws of electricity and magnetism. I'm going to write them all down and discuss them in the form that we've arrived at, the integral form. I'm actually jumping up to chapter 30 because I want to derive the existence of electromagnetic waves. Very, very important. And I'm treating it as though we just have as much time as we need. We'll do this, and then we'll use the remaining lectures, 2 or 3, to go back and do what we can do in chapter 29. Okay. And even in chapter 28, possibly some more. Okay. So this way we don't run out of time, right? We get to the electromagnetic waves, treat them properly. It's a hugely important topic. And then we'll see how much time we have left. Okay, so I'm going to write down the full laws of electromagnetic theory as we've discussed them, but we'll put them all on a board and see what we can see. So, we'll just title this The Laws of Electricity and Magnetism. This may be what I had on the board last time, but I think I'm taking an extra step. Okay, so the laws of electricity and magnetism, these are in integral form. We have Gauss's law, the flux of the E field through a surface is equal to the charge enclosed in that surface. Now, we've had Q over epsilon naught before. What I'm going to do is write 1 over epsilon naught integral density d volume. Okay. So this is a volume integral over a charge density, and of course, this equals Q enclosed, right? Density is charge per volume times volume is equal to Q enclosed, and as far as the boundary goes, this is a volume, so capital V, and this here, I'm just going to use this symbol. This little del in front of the V means the surface that bounds this volume. Okay, so you can put that in your notes. So this is Gauss's law. And it contains Coulomb's law, right? It contains the electric field expression when you just take a point mass in a spherical shell. And so it contains the electric field expression, and then if you know that force is Q times E, it contains Coulomb's law. Okay? And Coulomb's law, of course, is the basis of all electrostatics. So, contains E is equal to Q over 4 pi epsilon naught r squared times vector r, okay, directional vector. So it contains that. This is more general. The other one we've had was Gauss's law for a magnetic field equals 0. I'll say the boundary of a volume as well. So yeah, put that in your notes. That means just the boundary of a volume. So if this is a spherical volume, that's the shell that bounds the volume, okay, the surface. Good, so this is Gauss's law as well, and what it implies is that we cannot isolate a magnetic pole. And basically you have a source of magnetism, the field lines will curl around. You know, if they leave the surface, they'll come back in the surface, and so the net integral is 0. Okay. Then we have, maybe I shouldn't write so big. So what's our third one? We're going to write Faraday's law. Yeah, we'll put it right here. So Faraday's law, this is E dot ds. I'm going to describe these integrals a little bit more. And we're going to go ahead and put the surface integral right away. So it's minus derivative, time derivative of integral B dot dA, which is the flux integral. Now I think I had that in your notes last time. Hope I did. Did I have that in there last time? I think so. Actually, I can write I can just put this regular time derivative here. That's kind of a subtle point. That's all right. And here, this is through a surface, and this is through a curve that bounds that surface. So I'm going to say surface area A, and this is the curve that bounds that surface area A. Okay. And finally, we have okay, so this is Faraday's law. And finally, we have the Ampere Maxwell Law. And I'm not sure if I had that in the integrated form either. But let's go ahead and write it. This time, and by the way, we just did Ampere's law at the board, right? B dot ds. Now, instead of I enclosed, we're going to write mu naught integral J, which is a charge J dot d area, okay, through a surface, and then plus u naught epsilon naught. We got that time derivative, so d dt integral E dot dA. Okay, so this is pretty heavy on the integral theorems. So again, this is an area, this is an area, this is a curve that bounds that area. Okay, so this is heavy on the integral theorem, so I'm going to describe them a bit for you. And also, so this is the laws of electricity and magnetism. Also, to make it complete, we'd have to say we know that mass times acceleration of a particle, right, this is just Newton's law, force equals mass times acceleration, and the force for electromagnetism is QE plus QB cross B. So I've assembled everything we've done. Okay. So force on a charged particle in an electromagnetic field. That's just Newton's law. Mass times acceleration, there's the force. Okay, so what's to be said about these? Quite a bit, of course. But what I want to stress is that these are the integral form of laboratory experiments. Okay. For example, right, I said Gauss's law contains, this electric field, and by implication you take that and it contains Coulomb's law, which you can just test with charges and charges on strings and so forth. Okay. This one here is the experience that you cannot isolate a magnetic pole. Okay. Faraday's law also with coils of wire, currents, and things like that. These fluxes can actually be changed in time. This here, EDS, we usually see it as an electromotive force, as a voltage. But a voltage is a line integral of an electric field. So all of these things can actually be constructed, tested out in a lab with an actual physical apparatus. Okay. These constants here, right, this epsilon naught, that's just the proportionality constant that gives you the strength of the force, and this mu naught just gives you the strength of the magnetic field. Okay, so this is all laboratory based. Let's put that down as a note or two. So these formulas summarize experimental results. Okay. Experimental results. Laboratory results, if you will. What else is to say here is that, of course, that's some pretty heavy artillery in terms of your calculus education. So I'll just put a note here, another note. What we're looking at are the integral theorems, okay, or integration, vector integral formulas. Vector integral formulas, and I'm going to invoke some more of that material, because what we're going to do is use the formulas of vector analysis to turn these four equations into differential equations. So we should number these, huh? Number them 1, 2, 3, and 4. 1, 2, 3, 4. So they represent experimental results, right? They're heavy on the vector integration. And you know, when you do this in calculus, you realize these are pretty difficult to calculate in a concrete case, unless you have a lot of symmetry. But we're just going to use the vector integration theorems. We're not going to actually calculate something. So don't worry. So what we're going to do is to turn these into differential equations. So next, equations 1 through 4 can be changed or transformed, as the expression, transformed into differential equations. Now here's the interesting thing. Differential equations. The transformation into differential equations makes a certain assumption, right? This was all laboratory apparatus based. It makes the assumption that these laws hold true in an arbitrarily small region of space. Okay? Because we're going to change them into differential equations, which are just derivatives, you know, at some location. Whereas here we learned, you know, we generated these using apparatus and actual coils of wire and so forth. Okay? So that's a major theoretical step, turning them into differential equations. And we're going to do that because it's one of the major theoretical moments of all time. Okay, so we want to change these into differential equations. I'm going to demonstrate it for the first equation, and then I'll give you all of the basic formulas that you need, and I'll send you off in your summer vacation if you really want to work through every step you can. Okay? Nothing holding you back. Okay, so we're going to work on the first equation. So beginning with equation 1. Beginning with equation 1, we have to make use of Gauss's integral theorem. Okay, Gauss was pretty busy. Gauss's integral theorem. It's referred to as the divergence theorem. And the divergence theorem states that the integral of f dot dA, and you know what, I'm just going to use the symbol E, why not, okay. So the integral of E dot dA on this boundary of a volume, this surface integral, is equal to the divergence del dot E of a volume integral. Okay. So what we're looking at is one of the integral theorems of vector calculus. In a sense, they're like the fundamental theorem of calculus. Okay. Of a volume, okay, where divergence, I'll write it out, divergence of E vector is equal to the symbol divergence of E, and what it means is it's the sum of the partial derivatives, d dx of E sub x plus d dy of E sub y plus d dz of E sub z. So that's the operation, and if you have a vector, a flux integral, you can transform it into the divergence of E over a volume. Okay, so we're going to do that. I'm going to work right under here just to keep these things in sight. We're going to do that for all four integrals, but the first two integrals use the divergence theorem. I'm still going to keep the formulas on the board and work here on the right side. Now, what we have in equation 1, we have the integral. Okay, so we're transforming the left side into the divergence of E dV. So we have integral divergence of E d volume is equal to 1 over epsilon naught integral density d volume. Well, you'll notice we now have two volume integrals, and we can combine them. Integral divergence of E minus rho over epsilon naught d volume equals 0. Okay. But now the argument is this volume is arbitrary in space, and we can therefore argue that if this integral is over any old volume we choose in space, then the integrand itself must be 0. Okay. So V is arbitrary, therefore integrand vanishes, equals 0, therefore divergence of E is equal to rho over epsilon naught. Okay, so this is a differential equation. This was an equation with integrals. This is a differential equation as advertised. So I'm going to do all four of these. We can consult the clock. Yeah, I'm going to write all four of them down with enough commentary so you guys can go out and continue this if you want to. So this is the first differential equation. We're going to do all four of them. At this point I have to free up some space, which I'll do right here. So we end up with what are called the Maxwell equations. So equations 1 to 4 as differential equations. Also referred to as the Maxwell equations. And what we have is, we can even see what the second was going to be. So the first one is divergence of E is equal to rho over epsilon naught. Second one is clearly going to be divergence of the magnetic field vanishes. Now equations 3 and 4 are going to be a little different. We're going to have to use Stokes' integral theorem. And for that we're going to have the curl of E equals minus dB dt. I'll put a little commentary on that, but first I'm just going to write these down. And for the fourth one, for the Ampere Maxwell, we're going to get the curl of E is equal to, didn't write it down. Oh, I had it written down. I erased it right there. So the curl of E, we've got both, we're going to take both terms with us, I think. Yeah, we're going to keep both terms with us for the moment. That's curl of E, so the last one is curl of B. Eventually we'll drop some of this. Let's go ahead and, yeah, U naught J. U naught J plus U naught epsilon naught dE dt. So I have to give some commentary on these. These two were transformed using Stokes' integral theorem. Use Stokes' theorem. And Stokes' theorem is that the integral of a vector field, I'll just use any vector field, integral of the curl of a vector field dot the area, so the flux through a surface is equal to the vector field dot ds on a curve that bounds that surface. So A is a surface, dA is a curve. So do I have to write the curl out as well? We could. Yeah. So curl of some vector is defined as this symbol of that vector. And you can use a I hat, J hat, K hat. You can use a determinant formalism. This would be d over dx, d over dy, d over dz, fx, fy, fz. Actually a pretty complicated object. But the point is, using Stokes' theorem, and this isn't a force, this is just some vector field. Using Stokes' theorem on equations 3 and 4 here, you kind of see what happened, in fact, now that I have it up here. We reduce all of the differential equation, all of the integral equations to differential equations. And these are called the Maxwell equations. So yeah, at this stage of the game, what's the proof that these are true? Here, the integral form, we have laboratory apparatus and experiments. Here we have the idea that these laws hold in an arbitrarily small area of space, because these are defined as limits of difference, quotients, and so forth, as derivatives. So yeah, we have the curl, we have the divergence, okay? And those are the differential equations of Maxwell. Let's see how many minutes I have. Okay, I think we can pull this off. So from the laws of electricity and magnetism in experimental form, already generalized into these integral formulations, there's an assumption that they hold true in arbitrarily small regions of space, and then you assume that, and you can use these theorems of mathematics to turn those equations into differential equations. The next thing we're going to do is test them out for empty space, for space in which there's no charge or current. So we're going to rewrite these, and if there's no charge density and if there's no current, then we replace this with a 0 and this J with a 0. So this is Maxwell equations in empty space. So next, Maxwell equations in empty space. And that means that rho is equal to 0, so there's no charge, and J is equal to 0, so there's no current. No charge, no current. Because we have no trouble believing that, there may be a charge over here, but now we're out here this side of space and there's no charge, but we know there are still fields, okay? So we're not worried about that. But these simplify then, so now we have divergence of E equals 0, divergence of B equals 0, curl of E is equal to minus dB dt, and curl of B is equal to mu naught epsilon naught dE dt. So this is where Maxwell was in around 1865, the year 1865. And we want to start solving these things, and it's a pretty complicated setup. So what we're going to do, we can do the same thing in both of these. We're going to take a time derivative of both sides. Okay. Before I do that, I'm going to write down a couple integral formulas. Okay. Differentiation identities. So next, some identities. And actually, in particular, we need one. The curl of the curl of a vector, which I'm just going to call A, is equal to the gradient of the divergence. I'm going to write this out. Minus del squared of A. So this is the curl of the curl. This here is the gradient operator. And this del squared, it's called del squared, is the divergence of the gradient. divergence of the gradient. Basically, these are second derivative formulas, right? They get pretty wild in vector analysis. So we're going to make use of this, okay? The curl of the curl, and we're going to take the curl of the curl, so we already have a curl, we can take the curl of one of these, we're going to do it on both sides. Yeah. So now let's do this. Let's take the, now for equation 3, I'll keep numbering these 1, 2, 3, and 4, right? 1, 2, 3, and 4. So for equation 3, we have the curl of E is equal to minus d over dt of the curl of B. Okay, we're exchanging derivatives, no problem there. Okay. Now, what do we know about the curl of B? The curl of B is given by this expression here. So that's equal to minus d over dt times mu naught epsilon naught dE dt. Okay. So this is going to give us a second derivative. Got a minus sign there. Now, the curl of E, on the other hand, curl of E, that's the gradient of the divergence of E minus this del squared of E, okay? But the divergence of E is 0. So make a note of that. What we're left with is minus this del squared of E. By the way, the same thing, I just used equations 3 and 1. Exact same process can be used for the equations 2 and 4. Okay. And let's go ahead and see what we have here. We have minus sign canceling. We have this mu naught epsilon naught. I'm going to write things this way. D squared E dt squared is equal to, I'll divide over here, 1 over mu naught epsilon naught times this del squared E. And by the way, this del squared, let's write it out explicitly. That's d squared ex dx squared plus d squared ey squared d squared ez squared. Okay, but we're going to finish with this thing right here. So this is all theoretical work. This is the greatest theoretical work ever done, because what this is a wave equation. Okay. So all of these assumptions led to the idea that there could be electromagnetic waves. In other words, the electric field could propagate as a wave. Same equation, if you do these steps that I just did for the other two equations, you're going to get the same equation for the magnetic field. So the electric field and the magnetic field both satisfy wave equations. So electric and magnetic fields satisfy wave equations. So this is 1865. It was another over 20 years until this could be demonstrated in the lab. But what was so amazing about this in the meantime was this number 1 over mu naught epsilon naught, because in a wave equation, this expression that comes in front of the del squared E here is the speed of the wave squared. Okay. So 1 over mu naught epsilon naught is equal to, I'm just going to call it c right away, c squared, the wave speed squared, I'll write squared out, wave speed squared. And it turns out, and this was recognized at the time, this c here is the speed of light. So now the possibility is there that light itself is an electromagnetic wave. So this is the beginning of the huge explosion in everything wireless, and really there is not a greater theoretical moment in physics history, although there are a lot of great moments. Okay, this is one of them. Speed squared, so speed of light squared. I'm going to pick up with this next time. I have a couple good homework problems for you, in which you can actually, go ahead and calculate this out and see what's going on there. So let's formulate a homework assignment. These are all pretty good. Have to do with waves, and I'll probably discuss these at the next lecture as well. So homework 24. We're in chapter 30, right? We jumped to the end there. We're looking at problems 15, 18a, 43, and 45. So yeah, a couple of these are very basic. One of them is just to calculate this out and see what you get. One of them is very basic discussion of wave equation, one-dimensional wave equation. And a couple of these are about the Maxwell displacement current. Okay. So that's a good set. You'll enjoy it. Okay, good. See you guys next time.